Chapter 5, Section 1, the natural logarithmic function differentiation. Well, we're starting a new chapter, and our very first section has to do with the natural log function. We're going to do a little bit of pre-calculus, and then we're going to get to the differentiation of these natural log functions. But since we are starting a new chapter, I think you guys deserve a little congratulations. So as they say in Australia, give yourself a big clap. That's enough. Don't want it to go to your head. Okay, the natural log function comes into play because of all things, when we talked about the general power rule for integration, we were able to integrate x to the n dx as x to the n plus 1 over n plus 1 plus a constant, as long as n didn't equal negative 1. So we can't integrate x to the negative 1 power, but not using this rule anyway, this general power rule. What happens though if n is actually equal to negative 1? And of course, can it be integrated? Well, as it turns out, yes it can, just can't be integrated using the general power rule. So we have this definition, which is a unique looking definition, quite a bit different than the definition that we had in pre-calculus when we talked about the natural log function. We define the natural log function, the natural log of x, as being the definite integral from 1 to x. Notice that it's a function because it's going from 1 to x of 1 over t dt. The domain is the set of all positive real numbers, because you may remember you can't take the natural log of 0, you can't take the natural log of a negative number. The natural log is going to be greater than 0 when x is, the natural log of x is going to be greater than 0 when x is greater than 1. It's going to be between, it's going to be negative when x is between 0 and 1. And of course the natural log of 1 is equal to 0. You may remember this, and I'm kind of jumping the gun just a little bit, but the natural log of x is equal to y if and only if x equals e to the y. So now you can see why this number here cannot be 0 or negative, because e being a positive number, and again I'm kind of jumping the gun just a little bit, but you know a little bit about e being a positive number raised to a power, it cannot be equal to 0 or negative. So all these properties hold true. Now if we take this definition right here, and we apply the second fundamental theorem of calculus by taking the derivative of this. The derivative of the natural log of x is equal to the derivative with respect to x of this expression, the integral from 1 to x, 1 over t dt, which is equal to 1 over x. So we can take the derivative of the natural log of x and we get 1 over x, which is like our x to the negative 1, which tells me that if I try to reverse this process and I try to integrate x to the negative 1, it's probably going to involve the natural log function. But again, we're going to do a little pre-calculus review first, then we'll jump into some calculus here. So theorem, properties of the natural log function. The natural log function has the following properties: that the domain is the set of all positive numbers, the range are all real numbers. The function, and I've got it graphed over here, as you can see, it's continuous, it's increasing, it's going up and to the right, and of course it's 1 to 1, which means that it has an inverse function, and the graph is concave downward, as you can see from this. Now, some properties of logarithms, and this is not just for natural logs, but these properties apply for other types of logarithms, including common logarithms. As I mentioned before, the natural log of 1 is equal to 0. I should mention that if a and b are positive numbers and n is rational, then the following properties are true. The natural log of 1 is 0. The natural log of a times b is the natural log of a plus the natural log of b. The natural log of a divided by b is the natural log of a minus the natural log of b. And then this is kind of an extension of property 2, that the natural log of a to the n is n times the natural log of a. It's as if the exponent comes out in front. Now, some textbooks call these the laws of logarithms, and you should have these put to memory, because there are going to be instances when we will want to expand our expression, or there are instances when we're going to want to condense and write it as a single logarithm. So we're going to practice that just a little bit here. So let's try some examples. I can grab my piece of paper here to try some examples. Let's expand the natural log of 7/6. Well, the natural log of 7/6, this is going to be property 3 that I just had. Remember property 3. The natural log of a divided by b is the natural log of a minus the natural log of b. Well, this is the natural log of 7. minus the natural log of 6. Now I know your calculator can give you a decent approximation of this, but that's not what I'm interested in right now. I just want to expand it. On part B, I'm going to first write this as the natural log of 2x to the 1/2 power. Then I'm going to use property number 4 for the exponent, bringing the exponent out in front, that this is equal to 1/2 the natural log of 2x. And of course, the natural log of 2x can be expanded because that's using property 2, where we have a product here of two factors here, and we can write this as 1/2 the sum of the natural log of both of these factors. So this would be 1/2 times the quantity, the natural log of 2 plus the natural log of x. Now if you want to distribute by the 1/2 and get rid of the parentheses, that's fine as well. This guy here, this is going to use property 3 with the quotient. This is the natural log of the numerator, 5y, minus the natural log of the denominator, 3. But this first part is a product, so I can do property 2, which says that this is the natural log of 5 plus the natural log of y, and then of course minus the natural log of 3 on the end. And I've expanded it. Now I saved the best for last, as you can see. I've got a real mess here, but I'm going to start this off using property here with the quotient property, property 3. This the numerator, this is the denominator. I'm going to write this as the natural log of the numerator, which is x plus 1 quantity squared, minus the natural log of the denominator, which is x times the square root of x minus 2. I'm going to put that in parentheses for right now. Now this guy here, I'm going to use property 4 because I have an exponent. I'm going to bring him out in front. I'm going to write this as 2 times the natural log of the quantity x plus 1. And then I'm going to subtract. Notice here I have a product. So I'm going to put in parentheses here, or I'm going to use a bracket. I'm going to write this as the natural log of x plus the natural log of the square root of x minus 2, which I just write as x minus 2 to the 1/2. Now I'm going to get rid of those brackets, so I'm going to write 2 natural log of x plus 1 minus the natural log of x minus the natural log of x minus 2 to the 1/2. One more step, and I could have combined it, but do you see I have an expression to a power, so I can use property 4 and bring that exponent out in front. Now 2 times the natural log of x plus 1 minus the natural log of x minus 1/2 the natural log of x minus 2. And that's as far as I can expand that. Now, as I mentioned, the natural log is a logarithm that's base e. E is approximately 2.71828182846 and so on. It's an irrational number. It goes on and on forever and ever. Many years ago, in a classroom at a different school, I had a poster that had like over 4,000 decimal places on it. It's actually named E after the mathematician. Now I know that it looks a little bit like Euler, but it's actually pronounced Euler, the mathematician Euler. So you're a pretty big guy in math when you start naming numbers after you here. So we're going to define E. The letter E denotes the positive real number such that the natural log of E, which would be the integral from 1 to e of 1 over t dt, is equal to 1. And since the natural log of e is equal to 1, that means we have base e. That means that if I bring the exponent out in front here, that the natural log of e to the n is n times the natural log of e, which would be n times 1, which would be e. Notice the inverse, the canceling effect that's going on here. We're going to talk a little bit more about that later in this chapter. So now we've got enough to come up with the derivatives of the natural log functions. And this is the most basic one, and then this one involves composite functions, so it involves the chain rule. If we let u be a differentiable function of x, the derivative with respect to x of the natural log of x is 1 over x. X is greater than 0. The derivative with respect of x of the natural log of u is 1 over u times, chain rule, the derivative of u du dx as long as u is greater than 0. So now I'm going to differentiate this. So this is going to be property 2 here. This is going to be 1 over 5x times the derivative of 5x, which is 5. The 5's cancel. I just get 1 over x. Now, if you're wondering, well, how did that happen? How did I get back to the derivative of just the natural log of x? There's a 5 there. Well, remember, using the properties, this would be the same as taking the derivative of the natural log of 5 plus the natural log of x. And to take the derivative of a sum, it's the sum of the derivatives. Well, that's a number. The derivative of the natural log of 5 is 0. And the derivative of the natural log of x is 1 over x. So it works there. This case here, this would be 1 over 3x squared plus, if I get it right, plus 2 times, chain rule, the derivative of 3x squared plus 2, which is 6x. I'm going to write this as 6x all over 3x squared plus 2. It doesn't simplify. That's as far as I'm going to go. Now here I have to use a product rule because I have two functions. So this is the first one, x squared, times the derivative of the second one. Well, the derivative of the natural log of x is 1 over x, plus the second one times the derivative of the first one, which is 2x. Now I'm not going to leave my answer like this because it could be simplified a little bit. X squared times 1 over x is just x. And I'm going to put the 2x here because it's not 2x times x, it's 2x times the natural log of x. I'm going to put the 2x out in front and write this as plus 2x times the natural log of x. That's a much less confusing way to write that out. Here I've got the chain rule because I have a composite function. So to take the derivative, first with respect to the outer function, the exponent, that'd be 5 times the natural log of x to the 4th power, just the power rule, times the derivative of the natural log of x, the inside function, which is 1 over x. So I end up with 5 times the natural log of x to the 4th power all over x. Looks better that way. All right, let's try maybe 2 more here. Okay. All right, f of x is equal to the natural log of the cube root of x plus 1. I'm going to rewrite this as the natural log of the quantity x plus 1 to the 1/3. Now, if I chose to, I can use my property of logarithms and write f of x as 1/3 times the natural log of x plus 1. So f prime of x would be 1/3 times the derivative of the natural log of x plus 1. This would be equal to 1 over x plus 1 times the derivative of x plus 1, which is just 1. Or 1 over 3 times the quantity x plus 1. And that's my derivative. You can distribute if you want. So I'm going to kind of approach it the same way in part F here, problem number F. Problem number F. Boy, I can't believe I said that one. Letter F. I am going to take the derivative, but before I do, I'm going to expand this, and I'm going to write this as g of x is equal to, this is why we practiced it at the beginning. I have a quotient, which is a difference. I have a product here. I'm going to do it all in one step. Hopefully you will remember enough from your pre-calculus days that this will help you a little bit, but you can do it more in one step if you need to. I'm going to write this as the natural log of x plus 2 times the natural log of x squared plus 1 minus the natural log of x plus 5. That was what I would get if I expanded this out, as we did in some examples earlier. Now I'm going to take the derivative. This is 1 over x, that's easy, plus 2 times, this would be 1 over x squared plus 1 times the derivative of x squared plus 1, 2x, chain rule, minus 1 over x plus 5 times the derivative of x plus 5 is 1. So this would be 1 over x plus 4x over x squared plus 1 minus 1 over x plus 5. Now there's nothing really all that wrong with leaving your answer in that form, unless of course you have to find critical numbers or something along those lines. But you go to match your answer in the back of the book, and more than likely they have taken a couple of extra steps of algebra and they have written this as a single rational expression, which would mean you'd have to get a common denominator, which would be x times x squared plus 1 times x plus 5, and you would have to multiply top and bottom here by x squared plus 1 and x plus 5, plus you'd have to multiply top and bottom here by x and top and bottom here by x plus 5, so that would be 4x squared times x plus 5, minus, I might have to extend this fraction bar a little bit, I'd have to multiply top and bottom by x and top and bottom by x squared plus 1, so that'd be x times x squared plus 1. You do all this, you kind of hope that at least simplifies a little bit. I get x to the 3rd plus 5x squared plus x plus 5 plus 4x to the third plus 20x squared minus x to the third minus x all over my common denominator, which is x times the quantity x squared plus 1 times x plus 5. Well, this is a lot of algebra to do, but algebra is not that bad. Those cancel. That's kind of nice. These x's cancel. That's kind of nice. I get, let's see, 5x squared. I got a 4x to the third, though. Let me put that first. I like descending order. Then I have 25x squared. And then 5. So that doesn't look like that's going to factor. At least it's not going to factor conveniently. And that'd be x squared plus 1 times quantity x plus 5 in the bottom. And that would be more than likely what they'll have in the back of the book. So don't panic. You might want to get used to doing the algebra to rewrite this as a single rational expression, because there are times when that's what you're going to need to do, especially if you have to set the derivative equal to 0 and solve, because you're going to want that numerator. All right, now, there's another type of differentiation that involves logarithms, and you can see here it says find the derivative of y equals, look at this messy expression here. By the way, the other way to do this would be 1 over all of this times the derivative of all of that, and you think this was messy. That's really messy. And this looks like this is going to be messy. This looks like a quotient rule and a chain rule on top of it, actually 2 chain rules on top of this. But we're going to introduce what we call logarithmic differentiation. And to do that, notice there are no logarithms here, but we're going to take the natural log of both sides of this expression. The natural log of y equals the natural log of the quantity 2x plus 1 to the third all over, I'm going to have to get another pencil here, I'm going to write this as 3x squared plus 1 to the half. Let me get another pencil here, maybe a little bit sharper. Now by doing that, I can use, like I did up here, I can use my properties of logarithms to expand this. So I get, try to write this thing level here. So I'm going to write this as the actually I'm going to kind of do more than one step at the same time here. Natural log of the numerator minus the natural log of the denominator, but I have the exponent, so I'm going to write this as 3 the natural log of 2x plus 1 minus 1/2 the natural log of 3x squared plus 1. So now I have this equals this, and I have to take the derivative of both sides because I want dy dx. So the derivative on the left, because it's in terms of y, I have to use implicit differentiation, which would be 1 over y times dy dx. And then over here on the right side, this is going to be 3 times the derivative of the natural log of 2x plus 1 is 1 over 2x plus 1 times the derivative of 2x plus 1, which is 2, minus 1/2. Now the derivative of the natural log of 3x squared plus 1, that would be 1 over 3x squared plus 1 times 6x, the derivative of 3x squared plus 1. So I have 1 over y times dy dx. See if I can neaten this up a little bit. This would be 6 over 2x plus 1 minus 3x over 3x squared plus 1. And like I did before here, I'm going to rewrite this as a single rational expression. So I'm just going to kind of go out to the right here a little bit. This would be 6 times 3x squared plus 1 minus 3x times 2x plus 1, that quantity, over my common denominator of the quantity 2x plus 1 times the quantity 3x squared plus 1. Yikes! So I have 1 over y times dy dx is equal to, what a mess this is, that's 18x squared, and that's going to be minus 6x squared, is 12x squared. That's going to be plus 6, that's going to be a minus 3x, so minus 3x plus 6, I can pop a 3 out of there, all over the quantity 2x plus 1 times the quantity 3x squared plus 1. Now I could factor a 3 out of this, but I'm pretty sure that the trinomial I'd have left does not factor further, so I'm not going to be able to cancel anything. But I'm not done, because I want dy dx. I have 1 over y times dy dx. So to get rid of the 1 over y, I'm going to multiply both sides by y. So I have dy dx is equal to this big mess, which is 12x squared minus 3x plus 6, all over the quantity 2x plus 1 times the quantity 3x squared plus 1 times y. But what was y? Well, this was y, or is y. So this is the quantity 2x plus 1 to the third power all over the quantity 3x squared plus 1 to the half power. Yikes! This cancels with one of these. And these guys here, they're the same base, so I can add exponents. This is going to be a real mess. This is going to be 12x squared minus 3x plus 6 times the quantity 2x plus 1 to the second power all over, looks like 3x squared plus 1 to the 3/2 power. And again, you could factor a 3 out of here, but I don't think anything's going to cancel top and bottom, and I really don't want to expand that unless I have to try to match the back of the book, but that's what my derivative is. Now again, you got to weigh the options. Do you want to use the chain rules and the quotient rule, low d high minus high d low, or can you get away with something a little bit easier using logarithmic differentiation? Either way, you need to practice the logarithmic differentiation because sometimes that's an easier approach than it is to do it more direct. All right. Now, because natural log functions are undefined for x less than 0, you're going to sometimes see absolute value of u when you're taking the natural log of it because you want to make sure that it's not negative. So what we're going to do now is we're going to look at a derivative that involves an absolute value. And this is our last theorem in this section here, and it comes into play once in a while. Once in a while you'll see this on the AP test. It's worth remembering because every question counts. So let's put this one to memory as well, and it's very direct. It's very much like the derivative of the natural log of x. If u is a differentiable function of x such that u does not equal 0, then the derivative with respect to x of the natural log of the absolute value of u is just, and I don't see that, that's a prime there, u prime over u. Okay? Sometimes we think of this almost like du dx over u, or 1 over u times du dx. I kind of like u prime over u. It's kind of a nice way to write it. So let's find the derivative of f of x equals the natural log of the sine of x. Well, if I use this formula right here, which I've got to put to memory, f prime of x would be u prime over u. Well, this is my u. The derivative of the sine of x is the cosine of x all over the sine of x, which is the cotangent of x. Now, think about what we just did. We took the derivative of something that gave us the cotangent of x. I bet if we reverse this, I bet if we tried to integrate the cotangent of x, we're going to get something that looks like the natural log of the absolute value of the sine of x. But yet, I may have jumped the gun just a little bit. We're going to get to that later in chapter 5 as well. So practice these problems until you feel really comfortable with them. And of course, always ask questions when you're unsure.